So this is what we have discussed in the previous lecture, 7 crystal systems and 14 Bravais lattices in terms of these unit cells and the relationship that you have between the lattice parameters A, B, C and alpha, beta and gamma. Depending on their relationship and the interaxial angles or the spatial orientation, you can define 7 crystal systems, and depending on, apart from the corners where else you have lattice points, you can define 14 Bravais lattices. Okay. Now we have an important question to answer here as to what is the real basis for classifying lattices, whether these alpha, beta, gamma or A, B, C, these parameters, how they are oriented to each other, that is the shape of the unit cell, whether that is enough to classify lattices. Okay, so that is a very important question that we need to answer in order to understand crystal systems and crystal structures. And in order to answer that question, we'll again come back to this table of Bravais lattices and ask one more question as to why some of these boxes are empty, why some Bravais lattices are missing. So the answer to this question will lead us to the answer to the previous question, and once we answer that, we'll have more clarity in terms of the real basis of classifying lattices. Okay. So they say curiosity killed the cat, but when it comes to understanding scientific principles, curiosity is good, as we are going to see. So here we have the curious case of missing Bravais lattices, and we are going to see this curious case to answer the question that we asked. So as I said, we have certain boxes empty, some Bravais lattices missing. For example, if I consider the cubic structure, the cubic system, and ask why there is no cubic C, why there is no base-centered cubic. Okay. So if we want to answer that question, let us consider a unit cell of that structure. So this is a C-centered cubic unit cell. So here you can see two of them side by side. I will add two more in the front. And now let us also put the lattice points at the corners and at the center of two opposite faces. Okay. So here I have 4 C-centered unit cells of the cubic structure. Okay. Now I want to know whether this is possible, and you can find that, you can answer that whether it is possible or not if you see the other points and find the equivalence as to whether every point is equivalent to each other, right? So from a lattice point of view, if all the points are equivalent, then these points can constitute a lattice. Okay, and in this case we are considering a C-centered lattice. So if I choose these centered points and connect them, let us see what happens. So these are the 2 centered points I have connected. I will connect the other ones also. So this is what I did. What did I do? I have chosen a set of points because, as we know, unit cell is all about conveniently connecting a set of points within the lattice. So here, instead of the other points, I have chosen these centered points and connected them to find a cell. And now if you look at this cell, do you see the same C-centered unit cell that we have considered in the beginning? So here, where are the lattice points? We have lattice points at the corners, right? If you look at the blue cell here, and we also have 2 lattice points at the centers of the opposite pair of faces. So these points also form a C-centered lattice. So that means theoretically a C-centered cubic lattice is possible, right? But still we do not have that. So why there is no C-centered cubic Bravais lattice? So in order to answer that question as to why there is no C-centered cubic, we will consider the unit cell once again and examine it closely. But this time we will take 2 instead of 4. Okay, so these are the 2 unit cells of C-centered cubic lattice. Okay, and now what I am going to do, I am going to connect the points in this manner. I will connect one center point to a corner lattice point. Okay. If I do that, this is a cell, the blue color cell that can be sketched out from the same unit cell of the C-centered cubic. Now examine this cell, the blue color cell that we have in terms of the sides. These 2 sides, this and this, are half of the face diagonal. So if the edge length of the cube is A, this is half of the face diagonal. So that means this is A by square root of 2, right? The face diagonal is A root 2, right? So that is half of it. Similarly, this side also is A by root 2. And along the C axis, this is still A, isn't it? So we have a cell where A is equal to B, which is basically equal to A by root 2 in terms of the edge length of the cube. And here C is not equal to A and B. So this is a tetragonal structure, a tetragonal cell that we have created, right? And if you see this new cell, that tetragonal cell that we have is also smaller. The volume of the cubic cell is A cube, and volume of this tetragonal cell is half of that, isn't it? So this is a smaller cell. So for my convenience, I can choose a smaller cell and say that this is the unit cell of this structure, right? So here you can see that this is a tetragonal primitive cell, which is already there in the list of Bravais lattices. But if I go by this definition, that is the smallest unit or the smaller unit to be considered as the defining unit cell, then there would be problems, as we are going to see for another structure. Okay. So instead of calling this structure as cubic C, we can call this as tetragonal P or simple tetragonal if we consider a smaller unit cell. But if you go by that definition, as I said, there will be problems. For example, if I consider the cubic FCC structure, so I'll again take 2 FCC unit cells side by side. So let us put the other lattice points at the centers of the faces. So this is a FCC unit cell, and we have considered 2 of them side by side. Okay. Now, like what we have done previously, we'll connect these points, corner to face center, and see what is coming out. Can anybody tell me what is this new unit cell that we have created? Look at the lattice points. You can take it out separately if you want, and tell me what is this new blue color unit cell? What structure is this? Look carefully. All the lattice points that you have inside are part of this blue color unit cell. You will find one inside the cell, which is at the body center of this new cell, of this blue color cell. So apart from the corners, you have a lattice point at the body center, and we can see that this is a tetragonal cell. So here we have sketched out a tetragonal eye, or a BCT structure out of the FCC unit cell. So then, why both of them are there in the list of Bravais lattice? We have FCC, and we have seen that we also have BCT, body centered tetragonal. Then can we remove one of them, saying that these two are the same, and reduce the number from 14 to 13? We cannot do that, because this has been already found that 14 combinations can be there and you have 14 lattices. So that means if you take the unit cell shape as the basis for classifying crystals or classifying lattices, then you have a problem. It is not the real basis of classifying lattices, right? So then, what is the real basis? If we say that the shape of the unit cells in terms of this A, B, C and alpha, beta and gamma, if that is not the basis, then what is the basis? So first let us say that on the basis of the discussion that we had just now, we can conclude that unit cell shape cannot form the basis for classification of lattices. And this takes us to the same fact that we have considered before also while talking about unit cells, and that is, we have said that unit cell is not unique, because there are infinite number of ways one can connect the points and you can generate many unit cells in one given lattice, right? So unit cells are not unique, and now we have seen that how you can sketch out another type of unit cell from a particular lattice. We can now say that the unit cell shapes cannot form the basis for classifying lattices. So then we also need to answer, what is the real basis for classification of lattices? The answer to this is symmetry. You need to consider the symmetry and not the shape of the unit cell to classify lattices. Okay, and we are going to see what is symmetry. We will learn about symmetry, and then we are going to see how you can classify lattices based upon symmetry. Okay.